Hi class, so let's start with our class number 6. We're going to be talking about decision trees and ensemble methods. Decision trees is just going to cover yet another type of machine learning approach to both classification and regression problems, and ensemble methods are a slightly more convoluted approach to classification and regression problems in the way that instead of just using one single classifier, ensemble methods use multiple classifiers, trying to boost the accuracy of the algorithm. Okay, and again, ensemble methods will also see both how to apply them for classification and for regression. For ensemble methods, we will specifically look into 3 different approaches. Again, 3 of them, what their main contribution is the fact that instead of just working with one single classifier, we're going to be working with a set of them. But the differences between them, as we will see, is on the way they use the training data to build the different classifiers. Okay, so boosting will take one approach, and bagging and random forests will take another approach. And then random forests is just a specialization of the bagging approach, which also plays around with how features are selected. In any case, let's start with decision trees, and then we will move on to ensemble methods, and I will explain, the general idea and details about each approach. So, decision trees, the way to think about decision trees is imagine that you want to construct a set of rules to represent the data, right? A set of rules of the type if-then, right? You have if-then statements. You could think of a set of if-then statements as a tree. How? Basically, the if could be the one splitting the inputs into different categories, and the then could be the information behind the then could be the one used to actually assign values to those categories. Let's look at an example. For example, imagine that we have different x variables that can take real values. And imagine that depending on those values, the final label for the sample is going to be either true or false. Okay, this could be, for example, is the temperature high or low, or for example, is the food spicy or not. Okay, just think of problem in which the features are real values and the thing that we are predicting is just a Boolean variable, a yes or a no, a true or a false. So in this case, what we see is that we have, imagine if our input contains 3 different variables, x1, x2, and x3. What you see here is that the root of the tree, the top value, x1 larger than 5, that's the initial if condition. If x1 is larger than 5, what is it that we do? So depending on whether that statement is true or not, we will take one branch of the tree. So if it's true, we'll take the left branch, and then we'll evaluate another feature, whether x1 is larger than 8. And again, it will have 2 different branches going to either false or true label. And then on the other hand, if we go back to the root of the tree, the if rule in this case would be if x1 is larger than 5, but that's false, then we have other sets of conditions that basically continue creating nodes until the final labels are reached. So it's obvious to see how we can get if-then rules from this tree. The first condition that we see, the x1 larger than 5, would be if x1 is larger than 5. Okay, then we have 2 conditions, if it's true or if it's false. If it's true, then we see whether x1 is larger than 8, and we check whether that's true or false, and we return a given label. Okay, so that's the way that a decision tree can be translated into a set of if-then rules. Or the opposite, you might have a set of if-then rules, say in a medical, for example, in a medical setting where you have doctors create a set of rules regarding different medical conditions, you might be able to translate those if-then rules into a decision tree. So a little bit of practice. Imagine that imagine that we have created this tree. We have used training data and basically trained this tree, and that's the resulting trained classifier. And then we have an input vector with features that we want to basically understand, and we want to basically understand what's going to be the output label using this model, using this trained decision tree. Okay, so if you have, say, x1 equals 1, x2 equals 1, and x3 equals 1, how do we do it? So we start at the root and we say, okay, is x1 larger than 5? obviously x1 is 1, so it's not, so we go to the false branch. Then we check whether x2 is smaller than -2, because the label that we get is a true label. Okay, and you can do the same reasoning for the second example. And in fact, those are the labels that you will get. Okay, so this is how the whole decision tree process works. Okay, you have a training data set, you build the decision tree, and once you have your decision tree, you can use your testing data to basically put the features through the tree and understand what's the final label. I have already been talking about this, but basically there's a very specific terminology as of, what are the different components of decision trees. So we have the branches, which is basically each side of the split. So every time you have a given feature in the tree, that feature is going to branch out onto one or multiple different conditions, depending on the values that that feature takes. So those are the branches. And branches give out to new nodes, and then the tree is built until we reach the leaves. The leaves are the terminal nodes, are basically the nodes that return the labels, that return the values. Remember that in any supervised training scenario, we're going to have a set of samples that have features or labels, right? So the leaves are the ones representing those labels in a supervised setting. As I mentioned at the beginning of this class, trees can be used both for regression and classification. If we are talking about regression, the return value, the value in the leaf is going to be a real number. If we are talking about classification, then it's returning a class. And in general, decision trees are very easy to use, and they are, let's say, the pros about this type of predictive techniques is that they are easily and fast in terms of interpretation. Okay, so it's pretty straightforward. It's not a black box that we don't see what's going on, but rather, we exactly understand what's the role that each feature plays. This is, the classical example when we study the decision trees is the classical example as of should I play tennis or not? Okay, so what you do in order to understand whether you play tennis, you will probably collect a set of samples regarding the humidity, regarding whether it's sunny or rainy, regarding the strength of the wind, and then basically you will label them as play yes or play not. Okay, and with that training set, you can basically use it to build a decision tree, and this is a resulting decision tree. What this decision tree is saying is that once we had a training data set and we have trained it, it's basically saying that if it's sunny and the humidity is normal, you can play tennis, but if the humidity is really high, or if the wind is really strong, then you probably won't be playing tennis. That's what the tree has learned from the training data. But we can also interpret that as a regression tree, okay, decision tree for regressions. So how would that work? Basically, imagine that we have all the data points in the table. Same approach. So what we would do is basically take for each of the features there, is going to branch out with as many different values as the feature takes. So for example, for Outlook, we observe that there are 3 different values: sunny, overcast, and rainy. So, Outlook branches out to these 3. Same thing for sunny, okay? So basically, if it's sunny, then the next variable that we take into account is whether it's windy or not, okay? And if it's windy or not windy, depending on whether that's false or true, we assign an average number of hours played, okay? And for overcast, exactly the same thing. What we do is that we basically take all the samples that have overcast, and we compute the average. And for the rainy, exactly the same thing. We branch out depending on the values, and finally assign a given real value. Okay, the labels are real values. How these things are computed is something that we are going to look a little bit more into this class, okay? But in general, what you have to take into account is that given a set of different samples, we build a tree that we can then use for testing, and the tree can either output category labels or numeric labels. Right, so when you think about the decision tree, each internal node, it's basically testing an attribute, right? If we go back to this example here, say sunny or overcast or rainy, what they are doing is basically testing a specific attribute, okay? And depending on whether the attribute takes one value or another one, it basically branches out, okay? And the leaf nodes, I've already mentioned that too, assigns the classification value. In general, decision trees for classification can be represented as a function of x and y. Okay, so you could have things like, for example, x and y, or x or y, or x or y. Okay, so when we look at how a decision tree looks like, okay, what we are doing as we keep on branching out, basically we are looking into conditions, right? So if it's sunny and it's windy, then the final value is going to be 1. If it's rainy and the temperature is hot, then the final value is going to be another 1. Okay, so it's just a way of representing the information that we have in the tree. When should we think about using decision trees? So in general, whenever we have instances that can be described by attribute value pairs, okay, that's a good way or a good scenario in which we should be using decision trees. Okay, so think, for example, I have this set of attributes, and playing tennis might be a good idea or not. In general, decision trees can also cope quite well with noisy training data. Okay, assuming that noisy training data is not the majority of the data that we have, it can cope quite well with this if it's just a few points. And in general, you've probably come across decision trees in an informal setting. So, for example, when we talk about medical diagnosis, typically what doctors do in their heads is go through a decision tree, checking whether certain things are true or false, and they will basically diagnose something. Credit risk analysis, same thing. It's like a bunch of if-then conditions that they will test. Or, for example, modeling calendar scheduling preferences. Okay, so can these two things happen at the same time? Can one thing happen before the other one, and so on? So that's literally a decision tree. How are decision trees computed? So as usual in this course, what I keep saying in this course is that it's really important to understand beyond using different functions and commands in R. It's really important to understand what is it that we are running. Okay, so what I'm going to be explaining in the next slides is basically how decision trees are computed. Okay, internally when you execute any command. Is that something that you need to do for your milestones? No, but it's really important that you understand how these things are being computed. Let's look at the main loop. Okay, so basically the way a decision tree is computed is that, in an iterative manner, we are going to be looking for the best attributes. Okay, so we are talking here about whether it's, whether it's sunny or rainy. We're looking for the temperature. We're looking for the wind. So, these attributes, we have to choose which one is the one that we're going to use next in the tree. Okay. Once we have decided what's the best attribute to put not only as the root, but to continue exploring as we continue branching out the tree, the decision tree, we will use, in order to understand that, we will use entropy. Okay, and I will explain in a while how do we actually decide which attribute is the most important and how to use entropy for that. But basically, once we have decided that a given attribute is the one that we are going to use as a node, what we do is that for each potential value of that attribute, okay, for each potential value of that feature, so say for example we are looking, let's go back to the tree, we are looking at the outlook value. So outlook can have 3 different values, can be sunny, can be overcast, or it can be rainy, right? So what we do, the way this is built, is that basically for each of those values that the attribute can take, we create a new descendant node. And then basically what we do is that we sort the training samples in such a way that we reach the leaf nodes. Okay, and we continue doing that basically until all the examples are perfectly classified. Okay, or otherwise we continue adding nodes. Okay, so the way this works is, again, let's go back to the example here. Basically we start with Outlook. Why we start with Outlook, I will explain it in a second. But basically, once we start with Outlook, we create 3 different nodes, sunny, overcast, and rainy, because these are the possible values that Outlook can take. And then based on that, the way we decide what's going to be for example, how do we go from sunny to windy? The way we decide that, it's basically, again, using entropy. But let's imagine that we decide that, windy is going to be the next feature that we explore. Again, in this case, what we do is that we branch out a couple of nodes, which are going to be false or true, okay? And those nodes that we branch out, basically we cannot explore in anymore, and so we just assign the final regression value in there, okay? let's look at an example. So we've been saying that, so we keep taking each single attribute, and then based on, what attribute is the best to continue exploring, and then we create the nodes and so on. But how do we know that the attribute is best? So uh, let's try to understand this through an example. So if I show you something like this, let's imagine that we have an attribute which is A1 or A2. Okay, we have two attributes, A1 and A2, and we're trying to think which one are going to be using as the root of the decision tree. With which attribute do we start? Do we start with overlook? Do we start with windy? Do we start with humidity? So the way we do this is as follows. Basically, imagine that we have an attribute which is A1, and we have 29 positive samples and 35 negative samples of anything. Let's just imagine that we are in a binary problem. So basically what we have here is that if we use feature A1 as the root of the tree, we branch it out to the two potential values that it can take, and we observe that the initial samples are divided into two sets. One of them has 21 positive samples and 5 negative, and the other one has 8 positive and 30 negative. Okay, it's done a pretty decent job. Okay, most of the samples on the left-hand side are positive, most of the samples on the right-hand side are negative. If we look at feature A2, okay, we look that, the two nodes that have branched out, if we were to choose A2 as the root of the decision tree, on the left-hand side, we have a large number of negative samples, but we also have quite a few positive samples. And on the right-hand side of the tree, we do have, mostly positive samples. So if we were to look at this, the answer would be probably A1 is the best feature to go with, because A1 seems to separate better the positive from the negative. Remember that what we want to do with the decision tree is going to be a classification or a regression, right? So what we are looking for are features that fully separate, or that separate as better as possible the positive from the negative. Okay, so that's the reason why we would actually choose A1. Now, what I have just said in an informal manner is actually, or can actually be defined formally with a mathematical formula through the concept of entropy. Okay, so let me explain first what entropy is, and then we will talk about information gain. So if you think about having a sample of training examples, okay, S, and you think that those samples can be positive or negative, if what the x-axis here is representing is the proportion of positive samples that we have and negative samples that we have in S, so we can have 0 would be, we have no positive samples, so all the samples are negative, and 1 would be we have all the samples that we have in there are positive, there are no negative samples, okay? So basically, in the two extreme cases, the entropy is 0. Now, the tricky part comes when we have 50% of the samples positive and 50% of the samples negative, okay? Because the entropy there is going to be 1. I mean, we literally do not know what's going to happen, okay? I mean, it could be a positive or it could be a negative sample with the same probability. But in general, you can think of entropy, as how much uncertainty do we have in that sample, in that data set of samples, or what's the impurity, another way of putting it. Okay, if again the data set has only one type of samples, then we know that it's not entropic. If we start mixing things, then there's going to be some entropy. The formula that is used to compute entropy is what I'm showing here. So imagine that you have in a data set positive and negative samples. The entropy is computed as the proportion of positive samples multiplied by the log of that proportion minus the proportion of negative samples multiplied by the log of that proportion. Okay, and again, as I said before, all the entropies of all the samples are of one type. The entropy is 0. Now, why did I explain entropy? Because in fact, the way we choose, or the way any type of algorithm that you run to compute a decision tree, the way the algorithm chooses which features are selected as either the root or as consecutive nodes down the tree, it's basically using information gain. Okay, and information gain is a measure that uses entropy. So that's the reason why I explained entropy before. Okay, so basically the gain for a given sample, or for a given set of samples, okay, with respect to a given feature in that sample set, is the expected reduction in entropy due to sorting on A. Okay, so what this means is, imagine that we have a set of samples. Each sample has a set of features, and imagine that we choose a given feature, A, in that data set, okay? If we were to put that feature as the root node, how much entropy would we reduce from the overall entropy of the system? Okay, that's exactly what we are looking for. And it's just a way of explaining mathematically the intuition that I explained before with the example that is in this slide. So you have A1, you have A2. We are looking for the feature that better divides the samples into positive and negative. Okay, and so we are looking for the feature whose gain is the highest. Okay, because we want to reduce the entropy as much as we can. Okay. And why? Because of course the less entropy we have, the better the classifier will work, because we have more certainty about what's in the dataset. So basically the way we compute information gain is by first computing the entropy of the system and then basically subtracting the entropy of the nodes generated by having that feature as the root node, okay, for all the potential values that feature can take. And we're going to see an example in a minute, okay? But the important thing to understand here is that the way a decision tree is built is based on the information gain that each feature has. And what we mean by that is, with respect to the overall entropy of the data set, how much entropy are we reducing by using that feature as a root node? And we want to maximally gain information, okay? So we want to really maximize the reduction in entropy that we can get. So if we go back to this example, okay, the overall entropy of the system, how do we compute the overall entropy? So in this system we have 29 positive samples and 35 negative samples, so it's 64 samples in total. So the entropy of the system, it would be, again, is minus proportion of positive samples logged that number minus proportion of negative samples logged that number. So that's exactly the HS that we are computing there. Okay, so the entropy of the system is 29 over 64, that's the minus P positive, logged that value, minus P negative, which is 35 over 64. So the entropy of the system is 0.99. Now, what we want to understand is if we were to use H1 as the node to branch out, how much would we reduce that 0.99 entropy? And if we were to use A2 as that head node, how much would the entropy the overall entropy be reduced? So the way we compute this is again through information gain. So the gain for the whole dataset, given that we choose A1 feature, is 0.99, which is the entropy of the whole system, minus the entropy of the samples that we have on each of the nodes that have branched out if we were to choose A1. So if you look at what we have there, it's basically 26 over 64, because it's basically on the left. If we are looking into A1, okay, and then basically we see that the left branch of A1 has 21 positive samples and 5 negative samples. That's a total of 26. So we would compute 26 over 64, okay. And then within the parentheses where we're putting there, it's basically the number of negative samples that we have multiplied by the log of that, and then the proportion of positive samples that we have multiplied by the log of that. Okay, so that's the entropy for the node, the left node that has been created after branching out on A1. And exactly the same thing for the right-hand side branch. We would compute the entropy for that second node that is resulting from branching out on A1. And basically there on the right-hand side we have 38 different samples. So it would be the entropy for that node would be the proportion of positive samples multiplied by its log minus the proportion of negative samples multiplied by its log, which is exactly what you have there in the formula, right? So the gain for A1 is 0.27. That's information gain that we get when A1 is put as a root node. Okay, that's the reduction that we get in the full entropy of the system. If we do the same computation for A2, okay, information gain is 0.1. So in fact, what we reasoned informally, we reasoned that A1 apparently seemed to be dividing better positive and negative samples. We have computed that numerically. Okay, so by computing the information gain using A1 as a node feature to branch out, and by computing the gain for A2, we have realized that A1 appears to reduce more the overall entropy of the system than A2. So as a result, we choose A1 to continue growing the system. Let's look at an example, okay, of how would that work out in a practical example. Let's go back to the table where we have the different features. We have outlook, temperature, humidity, windy, and whether we play or not. By the way, by windy, false, and true, what this means is if it's false, it means that it's a weak wind. If it's true, it means that it's a strong wind. Okay, so which attribute is the best classifier? So how do we start building this tree? Again, we need to use information gain. Okay, we have to basically explore all the different features that we have there, and for each feature we have to compute its entropy, its information gain, and then basically the one that has the largest information gain is the one that we're going to be using as root node of the tree. So if you take humidity can be high or normal. And we have, for high, we have 3 positive samples and 4 negative samples. For normal, we have 6 and 1. And the same thing for wind. I mean, those numbers are coming from just looking into the humidity column and counting how many times when we see high, we see a no, and counting how many times when we see a high value, we see a yes in the play column. Okay? Always remember that then when we branch out, what we are considering is, how are we dividing the samples, but dividing with respect to the final label, which is the classifier that we want to build. And in our case, the classifier is whether we are playing tennis or not. So if we compute that information gain, you can go through this example again, at home. Try to make sure that you make these numbers and that you fully understand how this works out. But basically the information gain for humidity is 0.151 and for wind is 0.048. Okay, so what this basically means is that the information gain for humidity is much larger than information gain for wind. So we would start the tree with humidity. If we were just exploring these two, of course, okay? If another approach would be the proper approach is to actually look at all the different features, compute all the information gains, and then you'd probably realize that the one that we have to work with is outlook, okay, because it's the one that has the more information gain, and that's actually the reason why in the examples that we've seen, the outlook is the one that goes at the top. So imagine that we have already figured out that the outlook is the one that goes at the top. Basically, what in this other exercise we are looking into is basically, now that we know that outlook is the first feature, what would those 2 other features be? Okay, so we know that if outlook is sunny, then what's the other condition that we put? Okay, what's the thing that we put in the then and the next if then? Which attribute should we test there, where the question mark is? So it's easy. We can basically, what we have to do is compute the information gain for all the other features that we have. So for humidity, for temperature, and for wind, we have to compute the information gain given the samples that we have there. And we see that the information gain, the largest information gain is 0.97 for humidity. So then the next box there would be humidity. And in fact, if you go again and check the original example that I gave at the beginning of the class, you will see that humidity is in fact the next box that it's explored in there. So in general, okay, before we move on, that's the way, whenever again you run the decision tree algorithm, that is the way it's computed. Okay, so internally, the algorithm takes all the different attributes, all the different columns that it has, all the different attributes, and basically computes the information gain for each of the attributes with respect to the final classification labels, and the one that has the largest information gain is the one that we start with, and then we branch out with the nodes using all the different values that attribute can get, and we start again the process. So it's an iterative process. We repeat this until we are basically done. Okay, so ID3 was one of the first algorithms that was designed to generate a decision tree. C4, 5, and C5 were basically evolutions of ID3. Okay, so the way ID3 worked is exactly the way I have explained in the slides. So it starts with a root by looking at the best attribute using information gain, and it basically repeats. Once it branches out with the values for that attribute, it repeats the process until basically there are no more nodes to explore, there are no more features to explore. Now there's a bias in the way ID3 works, and in fact there's a preference for short trees, okay, and for those that have high information gain. So in general, because of the way ID3's decision trees are built, those attributes, those nodes that have a high information gain are the ones that tend to go at the top. Okay. Now the bias that we have in ID3 is basically a bias in the sense that some hypotheses are preferred with respect to others. So there's no bias in the sense that certain hypotheses are not being explored, but rather in the sense that there's a specific preference for a given type of trees. All of them are explored, but a preference to short trees is given. Okay? And in fact, it follows Occam's razor. So what Occam's razor says is that, shortest hypotheses tend to be the ones that fit better the data, as opposed to really long hypotheses. And here by a hypothesis, what I mean is if you start from the root of the tree, from the root node, and you branch down all the way to the leaf, okay, the shorter that hypothesis, so if you take just one of those potential possible paths down the tree, that's a hypothesis. So in general, Occam's razor and the bias that ID3 has is that it's going to explore shorter trees, so shorter hypotheses. So from the root node all the way down to the leaf, the shorter, the better. Why is that? Well, because in general, there are fewer shorter hypotheses, so it's going to be easier to explore and to build. And also a short hypothesis that fits data is unlikely to be a coincidence. Okay, so in general, if you have a really long hypothesis, it's highly probable that it's going to be a noisy sample. Whether if you have a really short hypothesis and you found that throughout all your training data, it's highly, highly likely that that's going to be a pattern in your data. Another important thing to consider with decision trees is overfitting. Okay, we already discussed the concept of overfitting. Basically, overfitting is a situation in which, imagine that we have a training data, we build our decision tree, and we have an error associated to the training. Okay, and we have also an error associated to the entire distribution of the data. So we would say that the model that we have built overfits the training data if there's another potential model whose error during training is larger than the model that we have, but whose error for the entire distribution of data is smaller. Okay, so what this means is that what might be happening in some cases for decision trees is that you can get a very good representation of the training data that you have and really minimize the errors during training. But then for the overall distribution of the data, for the entire distribution of the data, for your testing data, and even for the data that you don't see and you don't have in your data set, the predictive error there is going to be larger. Okay? And that's something that we want to avoid. This is just an example of overfitting. So you see the training data is the continuous line, the dashed line is the testing data. And what you can see is that during training, the accuracy is really good. But then during testing, as we increase the number of size and the number of nodes in the tree, you see that the accuracy, starts decreasing a lot. So we are losing a lot of accuracy in the decision tree as we start increasing the number of nodes. Okay, and that's precisely just because of the fact that probably we trained very, very, very well the hypothesis or the classifier, in the sense that we trained it to represent very well the training data, but not to incorporate other types of hypotheses. And in fact, that's what I was mentioning before about Occam's razor. In fact, what happens is that the longer your hypothesis, probably the more overfitting you might be facing, or your model might be facing. Okay, because the longer the hypothesis, the higher the chances are that that's going to be just a noisy hypothesis and it's not a pattern throughout your data set. So in order to avoid overfitting, you can either stop growing the tree when you observe that there's no improvement in the information gain. So remember that we are using information gain to continue pruning the tree. So if we see that by adding yet another feature there's no information gain, what's the point? Okay, let's not grow the tree anymore. And another way to do that could be to just grow the full tree and then basically post prune. So once it's fully grown, just prune the parts that might be inducing to error or to overfitting. How could this be done? So what you can do is basically split the training data that you have into training and validation. Okay, use the training data to create or to train your decision tree, and then you can use the validation data to evaluate the impact of pruning different nodes. So what you can do is, okay, I have this model, and then I'm going to take this small data set, this small validation data set, and I'm going to say, okay, what happens if I prune out, if I eliminate this node from the tree? If I eliminate this node, does the classification improve, or it does not? If the accuracy improves for the decision tree, then I can prune that node. It's not contributing with any extra information. And in fact, error pruning techniques have shown to improve the testing accuracy of decision tree. So what I'm showing here is just yet another dashed line, which basically shows how, as opposed to just having a simple test data, if we apply pruning after training the decision tree, we can actually slightly improve the accuracy during testing. And again, those are things that you need to know about, but that you will not be required to implement, because these are already part of the software packages that you run. Okay, so whenever you train a decision tree of any type, that decision tree basically is going to use the training samples to train the model, and it's also going to take a subset of those as validation, just to make sure that the tree is built as it needs to be built. Okay, so it's not only going to be using the training data to decide the features that go on each node, but also to decide on how to prune the tree. And I'm going to finalize this section by just talking about a few things that I have not mentioned so far. So ID3 trees are the simplest trees that you could think of, okay? But sometimes the attributes that we work with are slightly more complex than just a category. Okay, so sometimes the attributes we work with are continuous. So imagine that we work with temperatures. Okay, so a solution to that could be, in fact, to create categories out of the temperatures. So instead of working with real value numbers, you could work with conditions. If the temperature is higher or lower than X or Y, then that's true or false. That could be also a possibility. But sometimes we actually want to work with the continuous values. You know, in other settings, it might be the case that we have attributes with costs. So for example, medical diagnosis, blood test costs something. Okay, so every time we are going to have as a recommendation or as a label, take a blood test, that's an expense that we need to take into account. Okay, so how can we make sure that we learn a tree that's also consistent with low cost? Okay, so we want to incorporate into the features not only the gain, the information gain that feature will have, but we also want to incorporate the cost of adding that feature. Okay, so there are different techniques for that, and basically the way this is done is that the measure of gain is modified. And these are just two examples of how cost could be incorporated into the overall gain, and that formula there is the one that is used to explore the decision tree and to explore which features go into different parts of the decision trees. And also another issue that you might be facing, and that might be relevant also for your projects, is the fact that, you know, for some training samples, we might have a missing attribute. Okay, so some solutions that are typically taken is, you know, if you have basically, say we are testing a given attribute to understand whether we want to grow the tree in that attribute or not, we can just assign the most common value across all the other samples. So if we have a given sample that does not have a value for that feature, we can just assign the average value that all the other training samples have. Okay, or we could also assign the most common value among all the other examples that have the same target class. Okay, so not just take the average value, but rather the average value for those that have the same target class. Those are just approaches that, you know, you can take to solve unknown attribute values, to solve continuous attribute features, or to solve costs. Okay, in general, again, these are improvements, enhancements to decision trees that are already incorporated into software packages, and in fact, in this class, we'll be working mostly with C4.5 trees and C5.0 trees, okay? And those decision trees do have, the software packages that you will be running do have improvements for all the issues that we have just discussed. So you won't need to worry about missing attributes, because basically the algorithm can handle that by assigning average values. You don't need to worry about discrete or continuous attributes, because the software package will also handle that. You can even add costs if you want to do that. That's something that you want to add into your model. And, you know, the pruning is also taken care of. Okay, again, the important thing is that you understand what's going on when you run these packages. And the two slides that I just skipped, I mean, we have already seen that, and it's basically the fact that, how do you translate decision tree into a set of if-then rules or the opposite, and we have already seen that.